The next transformation that we need to explore are those of horizontal translations. And again, let's begin by supposing that we have a given function, y equals f of x, which again is going to be our parent function. This is our home base or basic graph. Now, the effect of adding a constant to or subtracting a constant from the x or the argument of the parent function is a shift of the parent function's graph, either left or right, respectively. So let's put that into some formal terminology. So we say that for some positive constant h, we have the following. So we say that the graph of y is equal to f of x plus this constant h is the graph of our parent function, but it's being shifted to the left h units. And in case 2, we say that the graph of y is equal to f of x minus this constant h is, again, the graph of our parent function, but it's being shifted to the right h units. Now, at first glance, these definitions can seem a little counterintuitive because we're shifting left when we're adding a constant and shifting right when we're subtracting a constant. So a helpful way to verify your horizontal translations is to think about how the x-intercept is being translated. So we're going to take the argument of our function and set it equal to 0. So we have x plus h is equal to 0, and solving for x, we can see that our new x-intercept here is at minus h, confirming to us that the graph is in fact shifting to the left h units. And very similarly, we can take the argument of case 2 and think about it in terms of the x-intercept. So we have x minus h set equal to 0, and solving for x, we can again see that we're left here with x is equal to positive h. Again, confirming to us that we are moving to the right on the x-axis h units. Now, to better appreciate these horizontal translations, let's go ahead and consider the following graph. To help us better understand horizontal translations, let's go ahead and graph the functions g of x is equal to x minus 4 cubed and h of x is equal to x plus 3 cubed. Now, before we get started on graphing, let's first start by identifying the parent function for both of these given functions and then describing the individual transformations for each of our given functions. So looking at our given functions g of x and h of x, we can see that our parent function for g and h is the cubing function, or f of x is equal to x cubed. And looking at the graph of this parent function, again, we begin by identifying a few ordered pairs on this graph so we can better appreciate how these points are being shifted along the x-axis. Now to begin, let's start by considering our function g of x is equal to x minus 4 cubed. Now looking at this function, since we're subtracting a constant from x, this means we know we're going to shift the parent function's graph to the right. So we can say that g of x shifts the graph of our parent function to the right 4 units. Remember, we can check our work here by setting the argument x minus 4 equal to 0 and then solving for x. So if we add 4 to both sides, this leaves us with a new x-intercept at positive 4. And since we're sketching a graph, we can write this in its equivalent ordered pair form, 4, 0. So that means looking at the parent function, we are taking its x-intercept and shifting it 1, 2, 3, 4 units to the right. And very similarly, we can take this ordered pair 1, 1 and shift that point 4 units to the right, producing a new solution point on our new graph, positive 5, 1. And again, with our second point down here, negative 1, 1, we are shifting this ordered pair 4 units to the right, producing the solution point 4, -1. And connecting these points with a smooth curve, we again can see here that the shape of the parent function's graph has not changed. We've just shifted over 4 units to the right. Next, let's go ahead and consider our second given function, h of x is equal to x plus 3 cubed. Now looking at this function, here we see that we're adding a constant 3 to x, which implies that we're going to shift the parent function's graph to the left 3 units. And again, remember here that we can double check our work by thinking about the new x-intercept. Or in other words, we can take the argument of our function h, which is x plus 3, and we'll set this equal to 0 and solve for x. So subtracting 3 from both sides, we see that we have an x-intercept here at -3, or in ordered pair form, -3, 0. So again, looking at the graph of our parent function, we take this x-intercept and shift it 1, 2, 3 units to the left. And we'll do the same sort of mapping here with our other 2 ordered pairs on the parent function. And connecting these 3 points with a smooth curve, we have the graph for h of x.